Hello again. This is Math 2232 coming to you from the College YouTube page, and the title of this lecture is Conic Sections in Polar Coordinates and Kepler's Laws. As always, be attentive while watching this video. By way of introduction, previously we've seen that rectangular equations for ellipses and hyperbolas, and parabolas for that matter, take simple forms when the origin lies at their centers. As it happens, there are many important applications of conics in which it is more convenient to use one of the foci as the reference point and have this position at the origin for the coordinate system. For example, we know that the Sun lies at a focus of the Earth's orbit. Similarly, the light source of a parabolic reflector lies at its focus. In this section, you will see that the polar equations of conics take on simple forms if one of the foci lies at the pole. Let's begin with an important theorem where we classify conics by their eccentricity. So here's the statement of the theorem. Let F, capital F, be a fixed point, and this is going to be the focus, that's why we call it capital F. And let D, capital D, be a fixed line, which is the directrix in the plane. So D is a fixed line. Let P, capital P, be another point in the plane, and let E be the eccentricity. And this E is defined as it was before. It's C over A in the other case, but that means it's the ratio of the distance between P and F, so that's between a point and a focus, to the distance between P and the directrix. The collection of all such points with a given eccentricity where E is a fixed number is a conic. Moreover, the conic is an ellipse if 0 is less than E is less than 1. The conic is a parabola if E equal 1. And the conic is a hyperbola if E is greater than 1. It's instructive to look at the proof of this, so we're going to talk about the proof. If E equals 1, that means that the distance from the focus to the point is the same as distance from the point to the directrix. Then by definition, it's a parabola. So that part is actually done already. Now, if E does not equal 1, then what we're going to do is we consider the focus to lie at the origin. So it's there. Without loss of generality, we can move it to there. And that's as shown in this. And the point P is up here. It's in polar coordinates, so that is R and theta. And if we're putting a focus there, then the directrix that's associated with that focus can be over here, and it can be a vertical line. And this is all without loss of generality. So this is 0, 0. This is the line x equal d, lowercase d. That's the setup we have. Okay, so for the point P, which is xy, but which is also r theta, we know that the distance from F to P is r. And we know that the distance from P to Q is, well, the distance from here to here is d, so the distance from P to Q is going to be, if I drop this perpendicular, here I get r cosine theta. So this is going to be d minus r cosine theta. And since we know that E is the ratio of this distance to this distance, it follows that I multiply both of these by the distance P to Q. I have this, so the absolute value, the distance PF is equal to the distance PQ times E. And so that means that we're going to be able to have that R here then is equal to, and this so this is this ratio times, and this is d minus r cosine theta. Now this, we can square both sides, And if we do that, we'll have r squared. This will be e squared d minus r cosine theta whole squared. So we can change that squared thing to rectangular coordinates. So this is x squared plus y squared is equal to e squared d minus x whole squared. So this is e squared, and then I just expand this d minus x times d minus x, and I get this. Now what we have here then is on this side we have e squared x squared. On this side we have this. So if I move everything to this side, the coefficient that I get here is 1 minus e squared for the x. Now usually we divide all the way through by that, and we do. And what we're going to do is we're going to be completing the square not on the y but on the x. So if you complete the square, and I encourage you to do this calculation, you get this. So x plus this coordinate squared plus y squared over 1 minus e squared is equal to this. Now this is not exactly the form of an ellipse, but if I multiply both sides, or if I divide both sides, I guess I'm multiplying. If I multiply both sides by 1 minus e squared whole squared over e squared 1 squared, I get 1 over here. And over here I get x minus a number plus y minus a number. And this number, both of those numbers are going to be positive. At least it's going to be positive as long as e is less than 1. So if e is less than 1, this equation is going to represent an ellipse. If e is greater than 1, then 1 minus e squared is less than 0. That means we get a minus sign, and I get a hyperbola. So we really have finished the proof of this theorem. And so when you think about graphing those things, if the distance from the point on the curve, in this case an ellipse, to the focus is less than the distance here, that means the ratio is less than 1, you get an ellipse. And notice that for this focus I get a directrix. For the other focus I also get a directrix. So there's actually two directrixes. There's one for each foci. If those two things are equal, well, this is just what we saw before. The distance from the focus to the point on the curve is equal to this one. That's a parabola. And here, if the distance from P to F is bigger than the distance from P to Q, then that's bigger than 1, and that's going to be a hyperbola, and you will get this configuration. So you get this for one focus, you get this for the other focus. Now notice that for each type of conic, the pole, that is 0, 0, corresponds to the fixed point focus in the definition. And that's a subtle point that some students don't remember, but you can always make it so by translating the conic to that place. So you translate the focus to that. So you can always study the shape of something by doing so. And the benefit of this location can be seen in the following proof of a theorem. And here's the theorem. And this also is an important theorem. It tells us what does the equation of a conic section look like in polar coordinates. Here's the statement of theorem, and we'll talk about the proof. So this is polar equations of conics. The graph of a polar equation of the form r equals ed 1 plus or minus e cosine theta, or r equals ed over 1 plus or minus e sine theta is a conic. And e is a number greater than 0. Now sometimes it will look like negative because of this plus or minus sign, but e itself is bigger than 0. And e is the eccentricity. And the absolute value of d, and this is the eccentricity times d, is the distance between the focus at the pole and its corresponding directrix. This is actually kind of an elegant theorem. I remember the first time I saw this theorem. I won't tell you the story, but I actually do remember that. Okay, so here's the proof. So what we're going to do is we're going to start, and we're going to, without loss of generality, we're going to prove it for the plus sign here with a cosine. with d greater than 0. So this is the figure that we set up. So here is our directrix. There is our focus. And this is the point P r theta that is on the conic section. And so I have this distance, and I have this distance, and so those are the distances that we're looking at. Okay, so consider a vertical directrix, that's this one, d units to the right of the focus. So from here to here is d units, and I see that it is d units up here. If P r theta is a point on the graph of r equals ed plus e cosine theta, the distance between P and the directrix, so that is between P and the directrix, is going to be d minus x, the absolute value of d minus x, because what's going to happen is the x coordinate over here is going to be negative, and so d minus x is going to be positive, so I'm adding that to that. That's the absolute value of d minus x, but that is d minus r cosine theta, because x is r cosine theta. And then what I can do is I can use this equation right here, and I can solve for d. So d, when I solve for d in this equation, I will get r times 1 plus e cosine theta over e minus, this is r cosine theta. Okay, so when you get the common denominator here, and the common denominator is going to be e, what will happen is that r e cosine theta will drop out, and I'll just have r over e. Now, because the distance between P and the pole is, this one is simply the absolute value of r, the ratio of PF to PQ is the absolute value of r over, and this was the absolute value of r over e. If you simplify this algebraically, you get the absolute value of e, which is e because it is positive. Well, okay, so what that means is that we have this number, so this graph must be a conic section. And the proof of the other cases is similar. So you see we have a standard polar form for these equations. Now, if we start graphing these, we'll see some similarities that happen too. If it had, and again, the pole is always at 0, 0, and that's always the focus. So this is 0, 0, this is 0, 0, 0, 0, and 0, 0. If we have a horizontal directrix above the pole, so this is horizontal above the pole, then this is the form r equal ed over 1 plus e sine theta, and we can see that here. If we have a horizontal directrix below the pole, here's the horizontal directrix that's below the pole, we get r is equal to ed over 1 minus e sine theta. Notice that if the orientation is vertical, then what I have is sine, the sine function. This is below and this is above. I think you can recognize the patterns that are happening here. If we have a vertical directrix to the right of the pole, there's the vertical directrix to the right of the pole, then this is going to be ed over 1 plus e cosine theta. And similarly, if we have a vertical directrix to the left of the pole, that means the directrix is x equal minus d. In this case, we get ed over 1 minus e cosine theta. So if your focus is being considered and your vertices are on the x-axis, you get cosines. If they're on the y-axis, you get sines. That is the axis that we're talking about. So those are the 4 types of equations that we can have. Let's apply that to this example 1. And as always, I would think that trying to work this problem would be a good thing to reinforce the concept. So what we're to do here is sketch the graph of the conic given by r equal 15 over 3 minus 2 cosine theta. Now, a key fact is that we need to have this coefficient to be 1 in the formula. And so what will happen is when this coefficient is 1, I have to divide all the way through top and bottom by 3 because I can't change the value of anything. So if I divide top and bottom by 3, I get this. You see, I'm forcing this to be 1. So this is 5 over 1 minus 2/3 cosine theta. I know this has to be E, and this has to be ED, so that actually tells me a lot. I know this is an ellipse, and E in this case is 2/3. Now, so what I can do is, so it's an ellipse, 2/3, so what I can do is I can go from theta equals 0 to theta equal pi, and I will get this top half of the curve, and then the bottom half I know will happen because of symmetry. Now, there are other things that you might want to know about, the A's and B's to graph these things, and sometimes you might want to graph them, even though they appear in polar coordinates, you might want to graph them using rectangular coordinates. So, in the example that we just did, the major axis is horizontal, and that means the vertices lie here. We're going to let theta equal 0 and pi. So this is 15, 0, and this is 3 in the direction of pi. So the length that we have there runs from, this is going to be 18, and that's twice the length of the major axis. So I know what A is. A is 9. And to find the length of the minor axis, we're going to use a couple of equations. We know that E, the eccentricity, which was 2/3, is equal to C over A, and we also know that B squared for an ellipse, B squared is equal to A squared minus C squared. So B squared is A squared minus C squared. That's A squared minus, and this then, if I use this expression, I know that C is A times E, and then I can factor the A squared out. This is A squared times 1 minus E squared. That's true for an ellipse. And just to solve this problem, we can figure out what B is then. So this is B squared is equal to, we figured out that A squared was not, A is 9, and so A squared is going to be 81, and this is 1 minus E squared, and that was 2/3. So we can figure out that that is 45. That means that B is the square root of 45. So the length of the minor axis then is twice that. It's going to be 6, the square root of 5. If we did a similar kind of analysis for hyperbolas, we would get that B squared is equal to A squared, and this is opposite. This is going to be E squared minus 1 because this has to be positive, and that's what we get for a hyperbola. And so you see we can find these other dimensions and actually do a very good job of graphing such a thing. Let's look at another example. So again, we're sketching a conic from its polar coordinates, and again, this is a good one for you to try. What we're doing is we're sketching the graph of the polar equation r equals, this is 32, and this is going to be 3 plus 5 sine theta. Now this time, when we divide all the way through by 3, we get 32 over 3, and this is coefficient here is 5 over 3, and that means this is a hyperbola. And we know from prior discussions that this is going to have and this is the focus that is 0, 0. And so what I can do is I know it's going to be oriented this way, and I can find the this is the directrix that I have. I know that the directrix is going to be at after I divide all the way through by the 3, the directrix is going to be at 32 over 5. And so the transverse axis, which goes from here to here, is 4 pi over 2 and minus 16. So that tells us that the distance is going to be, the length of the transverse axis then is going to be 12. And so A is 6. And to find B, we use the equation that we just derived for B squared equals A squared, E squared minus 1. We plug it in and we get 64, and that means B squared is 64. That means B is 8. And so we can graph this nicely using the these points. Again, make sure you follow these examples because these are the kind of problems I might someday ask you on an assessment. Not on the midterm, but perhaps on the final. Let's move on to talk about Kepler's laws. And by the way, Kepler was living on the Earth, and his observations on the Earth, which is very close to the Sun, and the Sun is the focus of the orbits. So anyway, Kepler's law is named after the German astronomer Johannes Kepler, and this can be used to describe the orbits of the planets about the Sun. He had three laws. The first law is each planet moves in an elliptical orbit with the Sun as a focus. Kind of an amazing thing. They're not circles, they're ellipses. And they go at different speeds through the orbits. So number 2 is a ray from the Sun to the planet sweeps out equal areas of the ellipse in equal times. Equal areas in equal times. And the third one is more complicated, but the square of the period is proportional to the cube of the mean distance between the planet and the Sun. Now that one is really pretty complex to think about numerically, but one of the things that I do when I teach Calc 3 is I derive these things. I assume Newton's laws and I derive that these are true. And in fact, Kepler just used empirical data and speculated those were laws, but Newton did validate them, and that's the vector calculus thing that we do in Calculus 3. And Newton did show that first, and in fact he also showed that to the English mathematician and physicist Edmund Halley, who came to visit him. And Halley is famous for talking about Halleys Comet. Now Halleys Comet has an elliptical orbit with the Sun at one focus, but you see if it's elliptical it means, oh, we see Halleys Comet, and then after a long time it comes back and we see it again. Its period is about 75 years, and Mark Twain, the great American literary figure, was born when Halleys Comet was in the air, and he claimed that he would die when Halleys Comet appeared again. And actually that prophecy turned out being true. Okay, so anyway, Halleys Comet has an elliptical orbit with the Sun at one focus and has an eccentricity very close to 1. 0.967. So that means it's a really very egg-shaped like that. The length of the major axis of its orbit is approximately 35.88 astronomical units. An astronomical unit is the distance from the Earth to the Sun, which is about 93 million miles. And that's what it's saying here. That's the mean distance. Because it is an ellipse, so it's not the same all the time. Find a polar equation for this orbit. And how close does Halleys Comet come to the Sun? Now, if you look at this graph, the Sun is at an axis, so you're really saying, how close does Halleys Comet come to the Sun up here? This is when it is most distant from the Sun, so we're really trying to figure out what this. Okay, let's look at the solution. Using a vertical axis, you can choose an equation in the form r equals ed, and this is 1 plus e sine theta. Again, we chose the coordinate system to look like this. Now the vertices of an ellipse occur when theta equal pi over 2 up here, and when theta is equal to 3 pi over 2. So we can determine the length of the major axis is the sum of the r values that we get from this. It's the r going this way and the r going that way. So that means that 2a is equal to, and I'm just plugging e and the sine of theta for those values into this equation. And the sine of pi over 2 is 1, and the sine of 3 pi over 2 is minus 1. So we substitute that in to get this. So 2a, which we knew was 35.88, so we just have one equation in D to solve, and we'll solve and we'll find out that D is equal to 1.204, and that means that ED is this times this is 1.164. So that's the value in the top, that's the product of ED. This is what the denominator looks like, and so we can find the closest point to the Sun. We figure out that C is E times A, because E was C over A. So that means that C is 17.35. That means the coordinate of the sun is 17.35. And c is the distance, so this is going to be 17.94 minus 17.35, and it's going to be this number of astronomical units, and that's this many miles. Make sure you follow some of this logic. Kepler's second law states that as a planet moves around the sun, a ray from the sun to the planet sweeps out equal areas in equal time. So when you're going here a long way from the sun, you're going slower because this area has to be the same as this area. But the only way that can happen is if this speed is slower than this speed. So you see it starts going faster here, then it's slower, 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 then it goes and then goes faster, and so on and so forth. So that is a ray from the sun to the asteroid Apollo, sweeping out equal areas in equal time. And so the closer it is to the sun, the greater its velocity. Here is the asteroid Apollo that we're talking about. So the asteroid Apollo has a period of 661 Earth days. And its orbit is given by this ellipse. And you can simplify this ellipse again. You see it as 5/9 there, but you can simplify that to be this equation, where r is measured in astronomical units. How long does it take Apollo to move from the position given by theta equal minus pi/2 to theta equal pi/2, which is shown in this figure? So you see here is the sun, and so what we have is this is the Apollo. So it's going around like that. And this is the, we're going from here, so that is theta equal minus pi/2 and pi/2. So we're really figuring out, the question that's being asked is how long does it take? What is the time it takes Apollo to do that? Well, we begin by calculating that area because it's equal areas in equal time. And so we're going to use our formula for the area, and we're going from, and that is 1/2 the integral of, this is r squared as a function of theta d theta. So that is 1/2. I put in what r is here. I square it because I'm squaring r, that is d theta, and go from minus pi/2 to pi/2. Now, when you start looking at this integral, it really is a pretty complicated integral, and you have to use the very fancy substitution, which I did introduce previously, u equal tan theta/2. And there was a student who came and talked to me about in the office hours about this substitution, and this is a complicated substitution, but we did talk about it before in an example, and the student asked me about the example, and we talked through it. And so using this substitution, we can calculate this, because this is 81 over, and then I just square all that, so I have a rational function in sines and cosines. So I can figure out what a is using that substitution, and I put the numbers in. There's a lot of calculation here, but we get it as 0.90429. Now, because the major axis has a length 2a, and we know what that is from this calculations that we have done, so this is going to be pi times ab, and these are the numbers I get for that. And so we know the area is 5.46, and so this is 5.46 is the area of this ellipse. But we know from Newton's second law that the time to complete an orbit was 66.1 days, so we can say that t is to 66.1 as the area of the elliptical segment. This little piece up here is to the total area of the ellipse. So it's this number divided by this number, which implies that t is equal to approximately 109 days. Pretty powerful stuff, and a lot of computational and serious math going on here. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.